Hello and welcome back to the Deep Dive. I was looking through the notes for today's session, and I realized something a little bit terrifying about chemistry.
Terrifying. Well, that's not usually the word we use for Unit 3.
No, hear me out. Usually when we study chemistry, we focus on the what. You mix acid A with base B, and you are destined to get salt C. It feels very fixed.
Like destiny, yeah.
Exactly. But the sources we are looking at today, specifically for chemical kinetics, introduce this variable that can basically, well, it can ruin everything.
Just talking about time.
Exactly. Time. Because, and here's the question I want to throw at you to start. Why is it that if I leave a glass of milk on the kitchen counter in May, in the middle of a hot Indian summer, it is spoiled by lunchtime?
It gets chunky, it smells bad.
Right. But if I put that same glass in the fridge, it stays fresh for 2, maybe 3 days?
It's the same milk. It's the same kitchen. But the timeline is completely different.
And then you go to the other extreme. We have all done that experiment in the chemistry lab with a magnesium ribbon. You hold it in the tongs. The teacher's yelling at you, don't look directly at it.
And then flash.
Yeah, it's instant. Blindingly bright white light. So here is the mystery we are trying to solve today. Who is controlling the clock? Why does the magnesium burn in a microsecond while the milk takes hours?
And rusting iron takes years.
That is the perfect way to frame it. We aren't just looking at chemical changes today, we are looking at the speedometer of those changes.
Which brings us to our topic, rate of a chemical reaction.
And this is from Unit 3, Chemical Kinetics.
This is the heart of the unit. And for the Class 12 students listening, this is a heavyweight topic. But, more than that, it is the bridge between theory and reality.
Well, that is my first challenge to you. Apart from getting good marks in the board exams, which, let's be honest, we obviously care about.
Right.
Why does a regular person need to understand rate? Why should we care?
Okay, think about a headache.
I have one right now just thinking about the syllabus.
Fair enough. But imagine you take a painkiller. What is your main concern? Not just will it work, but how fast will it work?
True. If it takes 10 hours to cure my headache, it is useless.
Exactly. If that pill dissolves and reacts with your body over, say, 12 hours, the rate is too slow, it's ineffective, you need a high rate of reaction, that is kinetics.
That is a good point. A slow painkiller is basically just candy.
Or look at the food industry. When you pick up a packet of chips and see an expiry date, that isn't a random guess. A scientist calculated the rate at which the oil in those chips reacts with oxygen to go rancid.
So they're using kinetics for that?
They used kinetics to predict exactly when that would happen.
So our health and our snacks depend on this. I'm sold.
I thought that might convince you.
Okay, let's get into the weeds. I am a student. I open my insert book, and I see this phrase, rate of reaction. In plain English, at the 0 level, what are we actually measuring?
At its simplest level, we are measuring speed. That's it. We are just asking, how fast are the reactants disappearing? Or, on the other hand, how fast are the products appearing?
Disappearing and appearing. Okay.
Yes, but here is where students get tripped up. It is not just about the amount of change. It is about the change per second.
Or per minute.
Or per minute, exactly. The time component is crucial.
Help me visualize this.
Yeah.
Because when I think of speed, I think of a cricket ball being bowled at 140 kilometers per hour. Molecules don't have speedometers.
No, they don't. So let's do a mental movie. This one is in the notes, and I love it because it is so simple. I want you and everyone listening to close your eyes for a moment.
Okay.
Picture a clear glass of water sitting on a table.
Got it. Glass of water.
Now, drop a sugar cube into it.
Okay. Plop. It is sitting at the bottom, a solid white cube.
That is time 0. Now, in your mind, just fast forward 30 seconds, look at the cube again. What do you see?
It's looking a bit fuzzy. The edges are gone. It's smaller.
Right. It is maybe half dissolved. Now, wait another 30 seconds. So 1 minute total has passed.
It's gone. Completely dissolved. The water is clear again.
Precisely. Now, if we wanted to calculate the rate, we aren't just saying the sugar disappeared. We are measuring how much sugar disappeared per second. We are tracking the speed of that disappearance.
Okay, so if it disappeared in 10 seconds, that is a fast rate. If it took 10 minutes, that's a slow rate.
Exactly. And if you had a magic microscope eyes and could look into that water, you'd see a very chaotic scene. We call this the molecular reality.
What does that look like?
Bumper cars.
Bumper cars, like at an amusement park.
Yes, millions of them. The water molecules and sugar molecules are just smashing into each other constantly. And every time they collide successfully, A reaction happens.
So old bonds break.
Old bonds break, meaning the solid sugar structure is destroyed, and new associations form with the water. The rate is just a count. It's how many of those successful crashes happen every single second.
So a fast reaction is basically a demolition derby.
That is a very good way to put it.
Okay, that gives me the picture. But before we move on, you mentioned a misunderstanding trigger in the notes. Something about how students confuse rate with amount.
Oh, yes, this is a classic trap. Imagine you are making rotis or chapatis for dinner.
I'm getting hungry again.
Stay focused. Imagine you make a stack of 100 chapatis. That is a large amount of product, correct?
Yeah, that is a feast.
But if it took you 10 days to make those 100 chapatis, was your rate fast?
No, that is incredibly slow, like 1 chapati an hour or something.
But if you made 10 chapatis in 5 minutes, your rate is very fast.
Even though the total amount is smaller.
Exactly. So on the exam, do not just look at how much product is formed. You must look at how much was formed per unit time. Rate is always about time.
That is a crucial distinction. It's not about the destination, it's about how fast you are driving.
Correct. So to make this stick even more, let's use some analogies. You mentioned driving, but the source material has a great one involving water.
The water drip analogy.
Yes, the water drip analogy. This is a standard way to think about it. Imagine a tap or a faucet in your bathroom.
Okay, picturing the tap.
If the water is rushing out at 5 liters per minute, that is the flow rate.
Correct.
Chemical reactions are the same. If reactants are being used up at, say, 0.02 moles per second, that is the reaction rate.
So if I turn the tap fully open, that is a high rate.
High flow equals a fast reaction. But if the tap is just dripping, drip, 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 that is a very slow reaction. It's quite intuitive.
What about the assembly line analogy? Is that helpful too?
That works too, yes. Think of a car factory. A manager doesn't just ask, how many cars did we make?
Right.
They ask, how many cars are we rolling out per hour? That per hour is the rate.
It really highlights that without the time part, the number is meaningless.
It is. And you know, historically, this was a big problem. In the 17th and 18th centuries, chemists knew that some things reacted and some didn't. But fast and slow are just too vague for science.
Right. You can't really do calculations with kind of fast.
Exactly. We need numbers. Without kinetics, which is the study of these rates, we couldn't predict anything. We wouldn't know how long a medicine stays in the body or how to plan a manufacturing schedule. That is why this concept exists, to put a number on the speed of change.
I want to give the listener one more mental movie.
Yeah.
We did the sugar cube, which is calm. Now let's look at something more chaotic. Let's go to the marketplace.
Ah, yes, the marketplace visualization. This helps explain why something like concentration affects rate.
So picture a crowded Indian marketplace. It is the evening rush.
It is packed. Lots of noise, lots of movement, people bumping into each other.
In this mental movie, the vendors, the people selling things, are the molecules, and they are trading goods. Every time a trade happens, that is a reaction.
Okay, so a trade is a reaction.
Now imagine the vendors start with red goods. Those are the reactants. And when they trade, the goods magically turn into blue goods. Those are the products.
Okay, I can see it. Red turning to blue.
If the market is super crowded, high concentration people are bumping into each other constantly. So what happens? More trades happen per minute.
High density means more collisions, which means a higher rate.
Exactly. And watching the reaction rate is like watching the market turn from red to blue. If the rate is fast, the whole market turns blue in a flash. If the rate is slow, you just see a blue spot here and there.
That is a fantastic way to visualize it. It connects the bumper car collision idea with the flow idea from the tap.
Okay, now let's ground this in reality again. We talked about milk and magnesium. Do we have other examples?
We do. Let's revisit that magnesium ribbon for a second because it is such a perfect observable phenomenon.
Right. In the lab, you light it and it just vanishes into white ash.
Yes. You see the magnesium ribbon turning into magnesium oxide. The speed is visibly fast. The reason is that at that high temperature of the flame, the collisions between atoms are happening so rapidly.
The demolition derby we talked about.
Exactly. The demolition derby is at full speed, so most of the magnesium is consumed in seconds.
Compare that to our refrigerator example.
Right. Why do we put food in the fridge?
To keep it from spoiling.
But why does the fridge stop it from spoiling?
Because it's cold.
Technically, yes.
Oh.
It's because at 4 degrees Celsius, which is your fridge temperature,
Yeah.
the spoilage reactions happen at a much, much lower rate than at 25 degrees Celsius, which might be your room temperature.
So we are effectively using temperature to put the brakes on the reaction.
That's a perfect way to say it. You're not stopping the reaction completely usually.
Yeah.
Spoilage still happens. It just happens very, very slowly. We are buying time.
Here is one that might trick people. Hydrogen peroxide.
Ah, yes. The counterintuitive example.
If you go to a chemist shop and buy a bottle of hydrogen peroxide, it just sits there, right?
Yeah.
It looks like water. Doesn't look like it's doing anything.
You might think it decomposes instantly because chemistry books always say it is unstable. But actually, in that dark bottle, it can sit for weeks or months. The rate is very slow.
But I've seen those videos, the elephant's toothpaste experiment, where people add something to it and it just explodes with foam.
Yes. If you add a catalyst, like a bit of manganese dioxide powder, it bubbles furiously in seconds. All that oxygen is released at once.
So the lesson there is,
The lesson is that rate isn't fixed. It depends on conditions. The same chemical can react slowly or instantly depending on things like catalysts or temperature.
that's a perfect segue. We have understood the concept, we've visualized it, and we've seen examples. Now, I want to switch gears. Let's go into mark-saving mode.
Let's do it.
We have some clarity lines from our source material. These are golden rules for the exam, but frankly, some of them confuse me. So I am going to play the confused student here.
Go ahead, ask the tough questions.
Okay, clarity line number 1. Reaction rate is always change in concentration divided by time.
Yes, that is the formula.
My question is about the units. What do I write?
Always check your units. Concentration is usually in molarity, so moles per liter. Time is in seconds, so the unit is mole the West.
Moles per liter per second.
Or you can just write millimolarity per second. If you forget the per second, you will lose marks.
Okay, noted. Clarity line number 2. Average rate versus instantaneous rate.
This is a common confusion. Think about driving a car again.
Okay, I'm driving.
If you drive from Delhi to Agra and you calculate your speed based on the total distance and the total time, that is your average rate.
Okay, so total change over total time. Simple enough.
But if you glance down at your speedometer at one specific moment to see how fast you are going right now, that is your instantaneous rate.
Got it. One is a span of time, one is a specific instant. That's clear. Now, clarity line number 3. This is the big one. Stoichiometry matters.
Yes, this is where most students lose marks.
So the notes say the rate of reactant A might not be the same as the rate of product B. But how is that possible? If I use up A, don't I get B? If I burn a log, don't I get ash? Shouldn't the rate be the same?
Not necessarily. We need to look at the balanced equation. Let's use an analogy. Let's talk about sandwiches.
I'm always happy to talk about sandwiches.
To make one standard sandwich, you need 2 slices of bread, right?
Right. 2 slices of bread, 1 sandwich.
So imagine you are a super chef making sandwiches. If you are producing sandwiches at a rate of 1 sandwich per minute, how fast is the bread disappearing?
Wait, if I make 1 sandwich, I use 2 slices. So the bread is disappearing at 2 slices per minute.
Exactly. The rate of bread disappearance is double the rate of sandwich appearance.
Ah, so the rates are different numbers.
Yes. And how do we know it was double? Because of the ratio, the stoichiometry. 2 slices for 1 sandwich?
So in a chemical equation, if I have a big 2 in front of reactant A and a 1 in front of product B.
Then reactant A is disappearing twice as fast as B is appearing. To make them equal, you have to divide the rate of A by that coefficient, by 2.
That sandwich analogy actually saves me.
Oh.
I was just going to assume all rates are equal.
Never assume that. Always look at the balanced equation.
Okay, final headache. Clarity line number 4. The negative sign convention. I look at the formula in the book. It says rate equals negative delta R over delta T. Why is there a negative sign? Speed cannot be negative. I cannot drive my car at minus 50 kilometers per hour.
You are absolutely right. The rate of reaction must always be a positive number.
So why the negative sign in the formula? That seems contradictory.
Think about the reactant. What is happening to its concentration over time?
Is going down, is decreasing.
So mathematically, the change is negative. If you start with 10 moles and end with 5 moles, the change is final minus initial, 5 minus 10 equals.
Minus 5.
Right. So the change itself is negative, but we want the rate to be positive. So what do? We put a negative sign in the formula to multiply against that negative change.
Oh, so it's like negative times negative equals positive.
Exactly. It is purely a mathematical patch to make sure the final answer comes out positive.
That makes so much sense. So I am never supposed to calculate a negative rate.
Never. If your final answer for a rate is negative, you have forgotten the sign convention.
And for products, do I need a negative sign there?
No, because products are increasing. Their change is already positive. so you don't need to fix anything.
Okay, that clears up the math anxiety. We have covered a lot. Let's do a quick short summary to wrap this all up for the listener.
Sure, let's recap the core idea. Rate is simply how fast reactants turn into products per unit time.
Remember the analogy. It is the water faucet. It is about the flow, not the size of the bucket.
And remember the visual, the crowded marketplace. Vendors trading red goods for blue goods. More trades per minute means a higher rate.
Remember the examples. The flash of the magnesium burning versus the slow spoilage of food in the fridge.
And finally, the exam tip. Remember the mnemonic COTT. COTT. Concentration observed over time tells us the rate.
COTT. I like that. Easy to remember. And always check your units.
Always.
Well, this has been a fantastic overview of the rate of a chemical reaction. It's really the foundation for the rest of Unit 3.
It absolutely is. Once you understand rate, everything else in kinetics order, molecularity, the Arrhenius equation, it all builds on this.
Before we go, I have a provocative thought to leave the listener with. We talked a lot about how fast things happen. We talked about slowing things down in the fridge. But is it possible to stop a reaction completely?
That is a deep question.
I mean, if we froze something to absolute zero, does the chemical clock stop ticking? Or does time just slow down infinitely?
Theoretically, at absolute zero, molecular motion stops. So yes, the rate would be zero. But can we ever truly reach that? It is something to think about regarding preservation and the nature of time itself.
Something to mull over while you were drinking your glass of milk? Hopefully fresh milk.
Hopefully.
Thank you so much for guiding us through this.
Thank you. It's a pleasure to break this down.
And to our listener, thank you for joining this deep dive. Next time you see a reaction question, just visualize that sandwich being made or the sugar cube dissolving. Good luck with your studies.
Goodbye and good luck.